Section 3.4 is talking about perpendicular lines, and a perpendicular bisector is a line that is perpendicular to a segment at the segment's midpoint. So we have to make sure that it's right at the middle of that segment and it's perpendicular, so it would form 90-degree angles. The distance from a point to a line is the shortest segment from a point to a line, and it's perpendicular to the line. So for example 1, name the shortest segment from P to AC, or to line AC. So if we're looking here, we want to go from P, which is right here, and we want to go to ABC, or AC here. So we have a couple of options. We have going this way, we have going straight down, and then we have going here on an angle. So what they're asking is what would be the shortest distance? Well, going straight there would be the shortest distance, so not going on an angle. So the segment PB is going to be the shortest distance. So PB, and we're talking about a segment, so we label it that way. Then it says write and solve an inequality for x. So if I look over here, what I do know from the previous example that we talked about is that x plus 3, that yellow segment, that x plus 3 is going to be longer than that PB, than that 5, because PB is the shortest distance. The yellow has to be longer. So x plus 3 is greater than 5. That's what I know. So then we're going to solve this inequality. So, not a 2, a 3. We're going to minus 3. And so that would be x is greater than 2. So it says write and solve an inequality for x. So we wrote the inequality, we solved it. X has to be greater than 2 in this case. All right, and then we have a couple of theorems here to look at. The first one says if two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So line L and line M cross. If they're perpendicular, then those two angles are going to be the exact same measure. So then that proves that L and M are perpendicular. If they're the same measure, they have to be 90 degrees because a straight line is 180. Then we have the perpendicular transversal theorem. So in a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So that only makes sense. If you have lines that are parallel and they're cut by a transversal, then that transversal is perpendicular to both lines. So we could say Q is perpendicular to P and Q is perpendicular to N because of the perpendicular transversal theorem. And then if two coplanar lines are perpendicular to the same line, then the two lines are parallel. So if those two lines form 90-degree angles with the transversal, then that proves that they're parallel lines because they would both have to form 90-degree angles to be perpendicular to the transversal. If one formed a 90-degree angle and the other one didn't, then they would not be parallel. They would eventually touch if we extended them. So they would both have to be parallel if they're both perpendicular to the transversal. And then we're going to use all of that information here to write a 2-column proof. And we're given that AD is parallel to BC, and that is indicated by those little arrows. We're also given that AD is perpendicular to AB. So AD and AB, the sides, the left side and the top, are perpendicular. And then BC is perpendicular to DC. So the right-hand side is perpendicular to the bottom side. And we have to use all of that to prove that AB is parallel to DC. So we're going to prove that the top and the bottom are also parallel. So we have to use some information here that we are given. And the first thing is that AD, line AD, is parallel to line BC, and that BC, since we're talking about BC here, BC is perpendicular to DC, and that is given. And from that, because this line and this line are parallel, and then this line and this line are perpendicular, we can also say that AD is perpendicular to BC because we were given these two are parallel. So if this one's perpendicular to this one, then this one has to be also perpendicular to this one. So AD is perpendicular to DC. And if we look back up, that is because of the perpendicular transversal theorem. So we're going to shorten that, perpendicular transversal theorem. Two lines are parallel, then they are going to be perpendicular to the line. All right, and then we were also given, we're going to use this piece of information, that AD is perpendicular to AB. So if we look at this, oh, I guess I got to finish this. This is given. I always put a proof there. So AD, this one here, is perpendicular to AB. Then we can say, we have to prove, our last thing here is to prove AB is parallel to DC. So we can say that, let me do that in a different color. AB is parallel to DC. So these, the top and the bottom, are parallel because we have proved that AD and BC are both perpendicular to DC. And if AB and DC are parallel, then they have to be perpendicular to AD and BC as well. So there's a lot going on in this little picture, and we just have to work our way through what we're given, what we know, and then where we can go from that. So to prove this, there's not a name for that theorem. We just have to say that two lines are perpendicular to the same line. So then, therefore, those two lines are parallel.